All right. Problem one. Okay, you guys should do this. Problem one is a circuit simulator. Basically, you are developing a simulation. Now, what probably throws some of you off a little bit is not just circuit simulator, but it's me asking you questions in the middle of it, right? So chances are a lot of you guys are overthinking those questions. All right, so maybe we'll talk about that a little bit today. This one is pretty similar to things that we've covered in examples. Problems 2 through 5 are, on applications, again, similar to things that we've done. They're not things that you shouldn't be able to do, but they cover things that are going to be probably a little bit weird to you in terms of the applications. So I wanted to run through that real quick. So problem 2, all right, chances are no one's gotten to that yet, I suspect. But basically you have that circuit that I've shown right there. That circuit is what I would call a high pass filter. Anybody know what that means? Any guess what that means? Sure.
Cut out low frequencies, so high frequencies.
Yep. You cut off low frequencies. Yeah. So this is a good reason. This is a good example of what a real signal would look like in the real world. That's an audio signal. All right. And if I looked at it, it's a sum of sine waves. Sine waves that are jumping up and down, right? Like again, I think I showed at some point, my voice, on the oscilloscope. That's what you see kind of jumping up and down. That's what this looks like. This is a sentence. It's about 4.5 seconds long. You'll hear the sentence when you go to play this the first time. So first of all, if you take the signal that I gave you in that .mat file that you'll open, all right, and you load it, and you plot it, it will not look like that. All right, it'll look actually more or less like a true sine wave. And when you play it, it'll sound like a bunch of garbage. All right. If you build your filter right, it'll remove the garbage and you'll hear a sentence when it's done. Right. So and this is the way that people do that. So you get signals that are corrupted with noise and you got to remove the noise. So you build what's called a filter. So one way to build a filter is the way that we're doing it here, which is to say I designed it, right? So I basically chose an R and a C value, right, that I gave you. And then I'm asking you to say, okay, give me the differential equation for that circuit, which you're not going to like. All right. Why do I know you're not going to like it? Because I'm asking you for the voltage across the resistor, right? That's a little bit different for you, right? You haven't thought about this yet, but the voltage across the resistor, right? Okay, so that's going to be the part that you have to think about how to do that. Now you know how to do this for the capacitor voltage. So the question is, can I relate that to that voltage across the resistor? All right. Now this is a pretty common thing to do because so I can take that analog circuit and I can convert it to its digital version of a filter, which is going to be a discrete time filter. Right. And so a computer doing processing like in a I don't know what's the Audacity or one of these kind of sound processing tools. That's what's going on inside there is that type of processing. But you can see where this, if I asked you for like what's the steady state response or whatever, you can see it doesn't really look all that steady anyway, right? And so being able to think about things in this context of discrete time kind of makes a little bit more sense anyway, rather than thinking of it in the context of there's a transient response and there's this guy had all kinds of wild stuff going on. All right, but it's a pretty real scenario. All right. And one thing I wanted to point out with this is it should be obvious to you, hopefully, that the whole choice of your delta t and everything actually in this case is fairly straightforward, because what I've told you in this case is that you have a sampling frequency, which is this value, 11.025 kilohertz. Now, what does that mean? What does it mean to say I have a sampling frequency? Anybody know what that means? So what this is here is this is a true analog waveform. Somebody spoke it. My speaking is creating a sound wave. That sound wave hits a microphone. The output of that microphone is an analog voltage, right? So it's continuous. To get that into a computer, to get that into a file, I have to sample that file, right? And so basically, if I look at something like this, so basically there was an analog to digital converter And you have that for a couple of problems in this particular assignment, right? So you're not dealing with the analog to digital converter, but there was one that created the file that you're given. Okay. So basically this dashed line here is the analog signal, meaning it was continuous at some point in time. All right. And it is sampled at regular intervals, right? So this t value here is 1 over f sub s, where f sub s is the sampling frequency. So if I sampled this guy at 11.025 kilohertz, then the time between samples is 1 over 11.25 kilohertz. All right. And what you end up doing to play the sound right, there's a command that it gives you, a MATLAB command that basically says, all right, you give it the name of the vector, and then you tell it f sub s. And when you do that, it's sending the samples in X to your sound card at that rate, right? So it should play, it's a wave file is what it is. So it should play like a wave file, right? But you have to tell it how fast to send it there, or else it's going to sound garbled. All right. But what that means is, in this particular case, is that the delta t value is known, right? What's the delta t value going to be? So when you go to get your discrete time equation, you're going to say, well, you know, dy by dt is approximately y of, what is it? How do I write this? Somebody other than, what's your name? I'm somebody other than Aiden. What is it? Yeah, t plus delta t here minus y of t. So what's that say? That's what? How do we express this in words? What is this? This is a slope, right? Yeah, rise over run, whatever. So y of t plus delta t and y of t, where are they relative to each other in time? Y of t plus delta t is later in time, right? These are basically subsequent samples, I call them. Remember, I said we have discrete time, I call them samples, the individual points, right? So this is basically, this is sample n plus 1, and this is sample n. So the fact that it's been sampled at 11.25 kilohertz or 11.025 kilohertz tells me what? Well, it tells me that I know what delta t is, right? What is my delta t? How far apart are those samples? What should my delta t be? Where would the next sample be relative to the current sample? What's the time between them? One over that frequency. Yeah. So in this case, I'm not trying to develop that simulation so I gave you a way to choose that when I'm doing that simulation, right? So which is thinking about, you know, something, the time step being much less than whatever sort of time domain features I'm looking for. In this case, I'm told that the samples are coming at me at that rate. So my delta t is set by that value, right? There is no data between, so whatever, I don't know, 1 over 11 kilohertz is probably on the order of somewhere between 100 microseconds and 10 microseconds. All right. And so that tells me that these values are coming at me. They're basically coming at me every 20 microseconds or something. I can't do anything faster than that. I couldn't choose a delta t any smaller than that. Yeah. So basically, I've been told in this particular case what value to use for delta t. Okay. Again, this is why I was trying to. The circuit I gave you in problem 1 is straightforward, and you struggled right in the differential equation. I know that, and it may not look straightforward to you. It's got switch in a weird spot, but it's a series LR circuit at the end of the day, right? You've seen that. All right. I know you've seen that with Yahoo, right? You saw that last semester probably, just not with an AC source, right? So this is one I know that'll take you a little bit of time. All right. I'm sure you do. You always do. Yeah.
Okay. So in the previous problem,
yeah,
you didn't give us the value of x of t. So
I did. But good question. I did. It's that. Yeah, right. It's that. Yeah. So I didn't say that explicitly. So yeah, thanks for asking that question. Yeah. So in fact, it's not even quite that. It's actually this plus noise. Some noise of t, whatever that is. I didn't show it to you because I wanted to show you this is what it looks like underneath the noise. If I showed you what it looked like with the noise, you would kind of just see a sine wave.
T is equal to Fs plus Nt.
No. The x of t is basically this signal plus some noise. And the noise I can tell you right now is, I don't know, so it's 10 sine, not that it matters that much, 2 pi 60t. So basically this plus 10 sine 2 pi 60 of t is x of t. So when I'm looking at this is a common way of doing filters. I'm looking at a circuit, getting a differential equation from the circuit, taking that circuit to a difference equation, a discrete time equation. And then my source, in theory, I could put this into a function generator and go into the lab and hook that function generator up to a circuit, and I would see something here at the output. In other words, my voltage source here is basically what I'm showing on the screen. In your case, what you're going to do is you're going to take this in a file and you're going to put it into a vector and you're going to run that vector through this thing. And you're going to get a vector y of t at the output. In other words, you're converting this thing into basically a math process where you're going to put in x of n and you're going to get out y of n. So you're basically taking this circuit and you're representing what nature does in a series of equations. Right? That's what you do in a computer, right? Is a computer, when it does digital signal processing, it's taking a physical process like this, which is governed by physics, and it's saying, all right, I'm going to take the physics and get the math from that physics so that I can play with that file. So I know I think that's a concept that you guys can understand. I mean, all the details of that are a little bit, beyond you, but I think in terms of how to approach this problem, I think you guys are well suited to being able to do that. Okay. Questions? All right. The third problem is, and the fourth problem is also communications related. So this is a communications problem. The thing that you'll need to understand here, this guy right here, this is called an AM wave. All right. So that's basically, when I say AM, what does AM mean? Amplitude modulation. What does it mean for something to be amplitude modulated? Any idea? What's that? Yeah, so its amplitude is varying according to something. So it's modulated. To say that you modulate something means that you control it. Okay. So now AM is not just like, angry talk radio or whatever. It's used for everything. Right. So I don't mean you to think, oh, this is old stuff. It's actually quite common. So like your cell phone is using amplitude modulation. In fact, your cell phone is using what I have here in problem 4, right? Which is actually a complex form of that. But what I have here is an AM wave, meaning if I were to look at cosine 2 pi ft, or this, if I were to look at this, what this is saying is somehow this x of t waveform, if I plotted it, it looks like a cosine whose amplitude is varying. So it would look kind of like this picture, right? And what I'm saying is I had an audio signal that I multiplied by some other signal. And that's what's happening. Like if you listen to, I don't know, 1100 kilohertz FM, or sorry, AM. So the 1100, if you tune the radio in the car to 1100 kilohertz AM, what you have is an 1100 kilohertz signal whose amplitude is varying up and down basically as somebody's talking, right? So what's happening here is this thing is called a demodulator. So what it's doing is at the end of this whole process, what is y of t here should be x audio of t. And it's a human voice that you should be able to hear. right? So basically what I ask you guys to do here is, I explained this in there, but what is that circle with the X through it, do you think? So I've got one signal, so this is an arrow, so there's one signal coming in here and one signal coming in here and another one coming out here. So what do you think this big X with a circle, or circle with an X is? What do you think that represents? What would an X represent as an operation? Yeah, it's a good thought. Antenna, it's not, but that's a good. It's a multiplication. It's saying that the two inputs are multiplied by each other. So I know that X out is going to be what? Yeah, it would be X of t, which is this input over here, times the other input, which is cosine 2 pi ft, like that. What would that be equal to if I plug in X of t? Yep. 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 Yeah, X audio of t times cosine squared, but I'm just going to write it this way as cosine 2 pi ft times cosine 2 pi ft. And what I say in the very first part of that problem is I ask you to expand this using Euler's identity, right? Which you know how to do, right? This is just like when we were doing those integrals where we had a cosine times a sine or a sine times a sine or whatever. This is the same sort of thing. And you're going to get an output from this. So I ask you to explain that output. Now, without going into the details, what I'm going to get is a low. When I multiply these two guys together, there's going to be two terms, right? There's going to be two terms added together that come out of it, right? Now, when you do that, I'm gonna have you look at what X out looks like, and what I tell you to do is that you need to pass it through what I call a low pass filter. So what do you think a low pass filter does? If a high pass filter got rid of the low frequencies, what's a low pass filter? Does the opposite. All right, the low pass filter gets rid of the high frequencies. So this circuit's second order, right? Obviously, but again, you also know a delta t in this particular case, because it's set by, again, a sampling frequency. So the data here, there's data that I give you, all right? And what I'm saying is you're going to take that data, load it in, you're going to multiply it by some cosine function. Then that result of that's going to give you X out, and then X out is basically what goes into this filter. So what you're doing again is you're saying, all right, I went and I did the design of this filter to basically be a low pass filter. And then you're basically saying, all right, I want to get the equations from that so that X out of n goes into your equations and comes out as Y of n. And if you do your stuff right, Y of n and X audio of n are the same thing. All right. So the audio, this is what you do. You take, so what kind of frequencies is the audio frequency? So when I'm speaking right now, what kind of frequencies? It's sine waves that are coming out of my mouth, right? What frequency range would they be in? Do you know? What's that? Yeah, so right. So first of all, let me ask this a different way. What's the highest frequency a human could hear? About 20,000, right? And the older you get, that goes down everything. A dog can hear to like 50 kilohertz, right? That's why dogs freak out over sound, right? Or dog whistles you don't hear because it's past the range you can hear. They're like 40 kilohertz. Right? So the human ear can hear up to 20 kilohertz. My speaking is lower than that, probably no more than like 2 kilohertz, right? If I had a high-pitched voice, right, then it would go to a higher frequency, right? But basically what it's saying is audio stuff is less than 20 kilohertz. The AM range, is somewhere around 1 megahertz, right? So basically what I'm doing is I end up taking that audio signal, which is low frequencies, and moving it up to a high frequency where it can fly through the air, basically. All right, that's essentially what's happening. And then when it's received, I need to take that signal that flew through the air, and I have encoded information into the amplitude. So then I'm going to pull it off. Basically, that's what this demodulators do, is pulling out the audio frequency so I can hear it again. All right. That's the basic approach. And to do it, you need to have a multiplier and a filter. And all this operation nowadays can be done in software. This is good software stuff. So there's things called software-defined radios, for instance. That's how I built this, is with a software-defined radio. All right. You know, anymore, the circuitry is the amplifier or whatever that interfaces between the antenna and whatever digital signal processor that's doing the hard work of what you have here. Okay. So the hard part here is this is a bit trickier problem, I think, for you guys, because again, this is a circuit. You got to write the differential equation, all that kind of stuff. But hopefully you can be able to figure that one out. Problem 4 is very similar. It's actually not. It may cause you problems, but it's not that hard. I'm basically just asking you to do a multiplication. Now the hard part is I'm asking you to figure. Hard part for you probably is going to be I'm asking you to figure out what to multiply by, so that X out here is equal to X audio directly. So you'll have to figure out what that is. All right. And you should, if you look at what X of t is, if I know that X out is really just X, what I call down here, X3 of t times X of t, right? I should be able to figure out what does X3 need to be so that X out is equal to X audio. All right. Now, the thing that's going to cause you all sorts of problems on this is the stuff I'm talking about, where I got to check the dimensions of these vectors when I do my multiplication, because if I got my dimensions wrong, it's going to be a mess. All right. When I say to get the dimensions wrong, remember what I was saying is if I don't check the dimensions, code's always right. So you may end up with these are audio files, right? That are several seconds long. They're big in terms of the number of data points in them. So if you goof this up, your computer may kind of go wander off for a while. All right, before it comes back to you. If MATLAB sits there for a while, doesn't come back to you, Control C over and over again, that'll be a quit. And it may take it a little while to respond to you, but Control C will kill it. Well, yeah. The Mosaic computers will still, you don't. But you won't break it. I mean, it's just gonna. It might blue screen it, right? I mean, I don't know. I mean, sometimes MATLAB is smart enough that if it's way beyond its capacity, it'll say, "Whoa, that was dumb." It'll say, this is going to be, a billion times a billion entries. So that's not going to work. The problem is when it can do it, because it'll just do it. And it's like, well, it's going to take up the whole memory, but that's what you wanted to do. That's when these are the sorts of things. Again, always pay attention when you're doing a multiplication like that, so you don't surprise yourself. All right, so that's why I mentioned this in there. So use that size command and things like that to get a sense of whether or not it's really what you think it is. All right, now the last one may be the strangest one for you, because basically what it's about is a DC motor. And it's a DC motor in a robot application. So I talked in the very beginning of the semester, I think when we started doing differential equations, I talked about, okay, if you had an embedded system controlling a robot, right, I might want to control the position of that robot, right? So when I say control the position, what I typically mean is, okay, I'll spin an actuator a certain angle, right? So I might have like an actuator that I want to spin exactly 90 degrees. The example I give you here, I want to spin it exactly 45 degrees. So basically, I'm having you develop the model for that. So what I wanted to do is explain briefly what it is. It's a second order system, all right, where it has a circuit model, which is what I've got right here. Okay. This is what a motor looks like if I do a cutaway of that motor. All right. There is a rotating part here, which is the shaft, and that would be connected to whatever the robot arm is, right? And then inside of that, I've got windings that are stationary. And on this rotating piece, there would be a magnet, okay? If I take a magnet and I had a coil of wire right? So I had a coil of wire and I ran a magnet. Let's say I ran a magnet through back and forth through the center of that coil. What would happen at the terminals? Well, I would generate a voltage for sure. And if I closed the circuit, I would generate a current. In other words, if I had a coil like this, very crappy coil, but I took a magnet and basically inserted that magnet and then pulled it out again, I would see a voltage right here. Now, what happens if I move that magnet faster up and down? I'll get more voltage, right? So basically, from a circuit model perspective, this is actually a situation where if I were to make a model of this thing, in other words, this isn't a model, this is a picture, it's a crappy picture. But if I made a circuit model of what this is, inside here, there would be a dependent source. So maybe I should draw that as a triangle and you guys, or a diamond, right? I should draw as a diamond so you're happier, right? But it's some constant times the speed at which I'm moving that thing. All right. So in the project, it defines omega as speed. And it's the speed at which this thing is rotating. So it's in radians per second. And again, no normal engineer ever talks in radians per second, but it's the SI unit, right? If I was talking about rotations, normally I'd talk about RPMs, right? Rotations per minute. I could convert that, but it's in radians per second. So basically, this is a case where nature gives me an honest to God dependent source, right? So if that magnet wasn't moving, there's no voltage. If it is moving, then there is a voltage, right? And how fast it moves controls how big the voltage actually is. So what I have is a dependent source. And then if I looked at this thing, it's got windings, right? So if I have wires, right? So like think about this picture right here. There's wires. So what do all wires have? Resistance, right? So there's some R in series with that. And I call it R sub A because we call this winding an armature. That's what we call it. That's where the A comes from. That's not all that important, right? Now it's also you'll notice that I've wound these windings around iron, right? So that means that this thing also has what? Inductance, right? So there's L sub A. So that's what a motor looks like, right? From a circuit perspective, from an electrical perspective, that's the model of a motor. And it tells me right there, if I spun a motor, I'd get a voltage. So when I spin a motor, what do I have? What do I call that when I spin a motor? Generator, right? It's generating something by spinning it, right? And I'd see a voltage. In this case, what I've done is I've actually hooked a source to it as well, where this is V sub A, like that. So V sub A of T is basically, that's this guy right here. This is V sub A of T. That is the voltage. That's the battery effectively that I've hooked up to it. All right. And that's making it do something in this particular case. So from this, I ask you to write a differential equation. How are you going to write the differential equation for that? What's that? KVL. You do a KVL to write a differential equation for that. It's pretty straightforward. And I said this guy's second order. Where's the second order? What's that? No, resistor is not a storage element, right? So it won't give me a second order behavior. So I get a second order behavior from looking at the fact that this guy is also a mechanical system.
Is it like a capacitor, almost like stores energy and dissipates?
Yeah. So what stores the energy? All right. So if you're driving along in your car and you let go of the brakes or you let go of the gas, right? You don't hit the brakes. Your car doesn't stop right away because it's got energy stored in it, right? Where's that energy stored in the car? What's storing the energy in the car mechanically? Well, so you guys are getting to be good electrical and computer engineers. So you're thinking about electrical stuff, right? But if I just think about the car as a mechanical system moving, Where's the energy stored in the car? So in physics 1, you learned all about kinetic energy and all that good stuff, right? So what's, yeah, so what's storing energy in a car? The mass. Yeah, the mass. Right? So once you're moving, there's a 1/2 mv squared, right, to that thing. 1/2 mv squared. There's a mass to that car that's storing energy. So there's another energy storage element in this thing, right? What is it? What's that spinning mass, right? So there's another one that comes from Newton's law. I just give it to you in this case. But what is Newton's second law? Is a good review. What is Newton's second law? Every engineer should know that. There's 3 of them, right? They're all about motion. I know what you mean. I know what you mean. That's the first one. That's the first one. What's that? That's the first law of thermodynamics. It's good. I mean, I'm glad I asked this question. Newton's second law, what is it? Yeah. What's that? Force times, okay, force. Yeah, basically, yes. It's the net force on an object is equal to mass times its acceleration. All right. Yeah. Bonus points for that. F equals ma, Newton's second law, right? That's what it is. Yeah. Yep. Not quite. I see what you're going with that, but it's, yeah, I mean, just in the context of a car, there'd be a motor to the car that would be driving the mass, right? And so there'd be an electrical equation or a set of electrical equations associated with the motor, and a set of them associated with the mass. In this case, this applies when I have linear motion. In other words, I'm moving in a line, right? A motor doesn't move in a line, does it? What's it do? It rotates, right? So here's a good question on that. What's the rotational equivalent of this? Torque. Yeah. So basically it's the net torque equals what? The moment of inertia times the rotational acceleration. Is that a term? You should have heard that term, moment of inertia. You may not think about it a lot, but it's the moment of inertia. So basically what I give you the equation. I say it's moment of inertia times the rate of change of speed is equal to the net force on that thing. So the net force is always the force applied minus the force against me. So in other words, if I'm moving a chair, across the floor, I am applying the force that's, if I'm moving at a constant speed, not accelerating, I'm applying the force that's exactly equal to the friction from the floor, right? So there's one force that I'm applying to go this way, and then friction's applying a force to go that way. So basically what I do is that's what's happening here is there's a force making this thing move, and there's a force trying to make it slow down. And the way I give that to you is the force trying to make it speed up and move forward is K times the current, some constant times the current, right? So once you know the current, you can figure out what force is being applied. And then there's a force of friction. So friction is related to what? What controls friction? If I were to push harder, wouldn't I feel more, right? So it's related to the velocity. So it's some constant times the speed. All right. So there's 2 equations. It's second order now. All right. So I've got 2 equations. One will come from here. One will come from here. Okay. Now, that is so that's why I wanted to look at this, because I think that's going to start to blow your mind a little bit. All right. Once you get in there. But if that's good. No, that's why I wanted to make sure you've thought about the fact that the problem one is something that you actually know how to do, right? You do and you don't know, right? That's is the thing, right? And I that's why I want to make sure you guys are starting those problems so that you realize that you do know, because I know what you guys do, which is to make everything harder than it needs to be, right? You start reading more into it. Like if it says get the steady state solution, get the steady state solution. Don't get the steady state and the transient. I didn't ask you for that, right? So I know, so it's a little bit different for you guys. So I want to make sure that you're thinking of it that way. You guys are trained in high school to the problem said this, so I have to do this, right? I'm asking you to step outside of that a little bit. Okay. Now, this one, if you get, and I know you'll do this, you'll get intimidated by the fact that this is something you haven't seen before, but you have. It's a circuit, right? I got to write a differential equation from that circuit. The other differential equation, I'm just giving you. It's this. This isn't a class about mechanics, right? So I'm just giving you that equation. And I give you the values of those things, the moment of inertia and the K and the beta and all that good stuff. All right. Now, don't be intimidated by it. Just treat it like it's a differential equation and you'll be fine. All right. So again, get moving on it. And on Friday, it'll be kind of an open office hours sort of time like I did on Monday. I want you guys to come in with questions. So it'd be good if you've been thinking about it ahead of time, right? And actually trying it. All right. Now, I guess what I'll do is record. I think I did this. This was the problem I did the other day, right, on Friday. And like I said, I didn't hit record. So I can go ahead and I can do it again, hit record, and just do that offline sometime and just post it so you guys can see it. But based on this, I mean, I guess I'll kind of stop it there. We don't have enough time to go into that. But if you guys want to ask questions now.